Okay, can you see the steam table? Guys?
Yes, doctor.
Good. Because I'm not sure whether you can. Okay, right now you are in this example. I'm not going to solve it. I'm just going to tell you how you're going to solve it because it's so obvious. Okay, if you look at this steam table, your temperature stated in the example is 127.2 degrees C, but it is not given at that exact temperature. You have to interpolate between the two values in this rectangle. Can you please just look at my cursor? Okay, you have to interpolate between 126.1 and 128.7 because the value that is specified is 127.2. It is not given exactly at that value. So you need to find the enthalpy of what? Saturated steam. So if it's saturated steam, then you'll be looking at steam, not water. You need to find that enthalpy. So that's the value somewhere there. Okay. And the specific volume, this is the specific volume of steam on this steam. So it's somewhere between these two, somewhere between these two values. Okay. And the temperature. So the temperature is between, where, not saturated. Oh no, cannot be finding the temperature. The temperature is already given. Only the, I think something missing here. Most probably is the internal energy. Anyway, find it and see whether you get the right. I'm not sure whether the answer is given, but you can find it and just do the interpolation. But I'm not going to ask you to do it now because you guys know how to do interpolation. So I'm just going to show you guys the example, and you can do it. Solve the example on your own free time. Okay. So let's look at another example. This is one example. Part A, find the enthalpy specific. There's the cap there with a subscript L. There's the enthalpy with a subscript L, and this is the enthalpy with a subscript V. So what does the L stand for? Anybody?
Liquid.
Liquid. Okay. So that means you'll be looking at water, the enthalpy of water. When it's V, you'll be looking at the enthalpy of steam. So the bar, the pressure is 30 bar, and luckily there's 30 bar. Okay, so obviously you just read it from the table. That is H, the enthalpy of L, liquid. That's the enthalpy of vapor, steam. So you just read it off the table. You don't need to calculate anything. Okay, so the answer is there. That's HL, that's HL, that's HV, that's HV. Okay. So next, the part B. Part B is at 45 bar. Well, 45 bar is not there. You need to interpolate. You need to find the saturated water. So you'll be looking at water. So you need to interpolate between these two values of 0.001266 and 0.001272 to get the specific volume at a temperature of 45 bar. Again, I'm not going to do it. I'm just going to leave it to you guys to do it yourself. Okay, the third part of the example, part C. Yeah, part C, your pressure is 60 bar. Okay, 60 bar is there. That's 60 bar. You have 500. That's 500. So you need to find the values for enthalpy. That's capital H, enthalpy. Internal energy, capital U. And the specific volume, V. So all of these values are for specific enthalpy, specific internal energy, and specific volume. So you just read it all from the table because, the pressure is there. It's stated 60. The temperature is 500. So you don't need to do any calculation. Just read it all from the table. So that's easy, very easy. Okay, so the thing that you need to do, if you look back at the previous part, is just for part B. You need to interpolate part B. Okay? So that's the only calculation that you need to do. For part A and part C, you just get it directly from the table. Any questions so far? No, anybody? No questions?
It's clear, doctor.
Okay, good. Okay, there's another example here. This is superheated steam. You need to find the specific enthalpy, which is capital H, specific enthalpy, at a temperature of 220. Unfortunately, 220 is not given. You only have 200, you have 250. Okay. The pressure is 0.1 bar. 0.1 bar is there, but the temperature is not there. That's 200, that's 250. You need it at 220. So you need to interpolate between that value of 2,880 and 2,977. Get it at a temperature of 220. Okay? You have the same bar, same pressure, but you don't have the temperature at 220. So you need to get that value, you need to get it at 220. Interpolate between 2,880 and 2,977. That's what you need to do. And the answer will be 2,918. You can do the calculation and check whether your answer is the same as given. Okay. For the second part, you already you need to get it at 220, but the pressure is at 0.2 bar. So that's going to be difficult because you don't have 0.2 bar, you have 0.5. For the second part of the problem, you need to do double interpolation. What do I mean by double interpolation? Just now, you managed to get 0.1 bar. You get that value for 220, that value for 220 degrees C. Now you need to get another value at 0.5 bar at a temperature of 220. So right now, look at my cursor, please. This is 220, for example. That's 220. So now, So what you have to do at a pressure of 0.2, get somewhere here, what is the pressure? Okay, this is, let me scribble something. You get that, oops, why is it not there? Okay, that is the value at 0.1 bar, 220 degrees C. That's after you interpolate. Okay, that's one value. Now at 0.5 bar, you interpolate at 0.5 bar at the same temperature of 220 degrees C. Same. Now what you have to do is find that value of enthalpy at 0.2. 0.2. You need to get 0.2. Okay? So you need to get the one in between 0.1 and 0.5. You need to do both the interpolation for 0.1 and 0.5. Then you can get 0.2. Any questions?
No.
No, good. Okay, so I'm not going to show you how to do it because you guys do know how to interpolate, but the answer for part B is that. So you can double check your calculation. So let's look at more examples. Okay. Whether we are going to do this or we're going to do the next one. Okay, this is more interesting. Okay, this is an example that is not from your textbook. We have a mixture. Okay, whenever you have a mixture, you need to look at if you need to calculate the energy balance, you need to look at the component. This is nitrogen, this is hydrogen. They are both gases. They have the form, the equation is N2 and this is H2. They are very similar. Structurally, they are very similar. So if they have similar structure, then you can assume that the enthalpy of that mixture is similar to the pure component. Okay, let's just put it this way. The enthalpy of this mixture, you can sum it up using the pure component. For example, this is nitrogen, this is hydrogen. So you can use the enthalpy of the pure component and sum it up, just like in for that mixture. So let me ask you guys, what is equimolar? What is equimolar?
0.5 mole of hydrogen.
0.5 what?
Mole of hydrogen per mole.
Mole per mole. Okay, mole per mole is percent mole. Okay, 0.5. So now your temperature is 25. That is 25. That's the initial temperature. And 1 atm. All this is at 1 atm. This table is specifically for 1 atm. Is fed to a heat exchanger. That's the molar flow rate. Heated isobarically. What is isobarically, please?
Constant pressure.
Good, thank you. and the final temperature is 200 degrees C. So 200 degrees C is there. Okay. So what you have to do is calculate the heat required. So you need to get from the initial temperature, the value of the enthalpy, and also the value of the enthalpy at the final temperature. Okay, so I need to use my iPad in order to show you guys the calculation. Let me connect to the computer. I hope I can get it connected. Before that, I need to unshare this so that we can look at my iPad. Okay, this is not the example that I want. Where is the example? Okay. Can you guys see the screen, please? Can you see the screen?
Yes,
Yeah.
Yes, yes.
Is it too small?
yes.
Can I enlarge it?
You
Not
can
sure that
zoom
I
it in a bit.
You can enlarge the screen on your side, isn't it? Can you or can't you?
Yes, yes, we can. Okay.
Good. Okay, now I enlarge it. Okay. So let's see how to start. First thing first, what do? You are given this question. What do you do? What first? What have you
Choose a reference. Choose a
So-
reference.
The
reference?
basis.
Reference.
Basis.
Reference.
Basis.
Basis. You need a basis. Okay, your base. Oh dear. Basis. Good. Now it's very large because I zoom it up. Okay, basis should be
100 mole per minute.
100 mole per minute. Okay. Now I need to really draw what next? I need to draw, isn't it? I need to draw the diagram. I need to I need to reduce the size because it's too large. I cannot use the rest of the page. Oops. Oh dear. Hold on. I'm not doing very well here. How can I? Okay, good. Not too big because I need the space. Okay, I need to draw the diagram. Okay, I need to draw the diagram. Before you can do anything, you need to draw your block diagram. Over here, you have your input coming in at, the molar flow rate. The molar flow rate is 100 mole per minute. This is fit. Coming out, since it's just a heat exchanger, so the same amount should be coming out. Nothing is going to, it's just one stream in, one stream out. Next, what do you need? You need the temperature. You have equimolar 0.5 mole per mole of high nitrogen. And the same thing, 0.5 mole hydrogen per mole. That is your molar flow rate. The same thing on the outlet stream. The composition is the same, nothing changed because you only have in and out. One stream in, one stream out. Right, so that's hydrogen. Okay, you have this equipment is a heat exchanger. So you are heating up the mixture from a temperature of 25 degrees C to 200 degrees C. Okay. So what's the amount that you need to put in? That's the question. What's the amount of heat that you need to put in for this heating process? So what you have to do when you do this problem, so I'm going to go to the next page. Yeah, but looking at the diagram just now, okay, you have the diagram there, it's visible. Okay, so what I have to do is, first of all, before I can solve for the energy balance, what do I need to do?
Write the equation.
Write the equation. What equation?
First law of thermodynamics.
First law of thermodynamics.
What is the equation?
Open systems.
Open
First law.
system. Thank you. Open system. So it's delta H. That's the change in enthalpy, the change in kinetic energy, the change in potential energy. Remember, you have the dot there. That is equals to Q dot plus the shaft work with the dot there. Okay, I need to make the dot bigger. Okay, since it's a heat exchanger, you're not going to have any kinetic energy. You're not going to have any change in kinetic energy, no change in potential energy. So that's going to be 0. And there is no parts moving inside your heat exchanger. Your shaft work is going to be 0. Okay, so you end up with Q is the unknown that you need to solve. Your heat supply to the heat exchanger is equals to the change in the enthalpy. And the change in the enthalpy, if you remember back how we solve it, outlet, that's since we're looking at mole, so this will be molar flow rate times by the specific enthalpy minus the outlet in molar flow rate and specific enthalpy. The sum of the molar flow rate times by the specific enthalpy. So if we do a table, okay, we're going to do a table, but before that, what is the reference state? We need to specify the reference state. What is the reference state?
1 atm 25 degrees C.
Okay, why did you say that?
Because enthalpy and internal rate at 0.
Yeah. Okay, because you're going to use these values, the values of the enthalpy are from the table B8. So the reference state is specified here. This is the reference state, gases, that's the pressure, 1 atm. I delete it just now. So that's your reference state. So you need, if you are using that table to solve your energy balance, then you need to use the same reference state as that table. If you're using the steam table, then you have to use the reference state of that steam table. Okay? So if you have many tables that you're using to solve your problem, you have to have the same reference states for all the table that you're using. Okay, so if you're using, for example, a different table to get your enthalpies, then you have to have the same reference state for all the tables that you're using. So in this case, there's only one table, so this is your reference state. So we're going to go back to that page again. So reference state is going to be gas. The phases is gas. Pressure 1 atm. Temperature 25 degrees C.
Doctor, I want to ask,
Yes?
is it compulsory for us to write the reference state on every question?
Yes. If you do not write it, then you will be missing some points. You have to, because whenever you do energy balance, remember you are doing change in enthalpy or change in internal energy. So you need to have reference state. Specific enthalpy and specific internal energy cannot be, the value cannot be an absolute value. You cannot calculate it directly. It's a change value. It's a state function. So you need to have a reference state. Thank you for the question. So now let's do our calculation. I'm going to get it. Okay, no, sorry. I'm going to write. I want to write a table actually. Why can't I write a table? Oh dear. My pen is not doing the writing up again. Same thing as yesterday. I need to get another pen. Okay. There. What happened now? It's too slow. Erase it. Let's see whether I can draw it. Something is not right. Okay. What I'm going to do is I'm going to draw a table. Let's see. This is what you normally do. This is for your enthalpy. This is for nitrogen. This is for hydrogen. This is N with a dot in. This is N dot out. I should erase that. I need to make it bigger. Okay. It's slow, but we're getting there. Okay, that's in dot there, dot here. A specific enthalpy in, specific enthalpy out. Okay, go back to our diagram. 100 mole coming in, 50% of the mixture is nitrogen, 50% of the mixture is hydrogen. So what's the amount of nitrogen? Sorry, what's the amount of nitrogen coming in?
50 mole.
50 moles per hour.
Okay, write the unit actually, mole. What was the unit just now?
Per minute, more per
Per
minute.
minute. Okay, per minute. So I need to write per minute. I don't have enough space there. Per minute. Okay, not. I need not doing well here. Not enough space. Okay, 50 mole per minute. 50 mole per minute. Okay. How about the outlet? I really need to write the unit, mole per minute. Beside. Okay. So what is the amount coming out?
Should be the same.
50.
Same.
Okay,
Same.
it should be the same. All right. Now, the enthalpies. Now, we're going to go back to the table. Yeah. The enthalpy for temperature of 225. Sorry. I have to delete that. Okay. Oh dear. I didn't do good. Now, 25. Put. I miss it. 25. Where is nitrogen? Where is my nitrogen? I think this is nitrogen. That is hydrogen. Is that right? This is nitrogen, 0. That's 0. Okay. The other temperature, 200. Okay. That is the value. And that's the value. Okay. Let's, have you got the e-learning, the notes from e-learning, guys?
Yes, yes, doctor.
Okay. Did I got it right? Nitrogen, is this nitrogen? This part, is it nitrogen? Check, please. With the notes from your the slide from your my e-learning.
Yes,
That's
yes,
nitrogen. Yes, because I erased it just now. I accidentally erased. So this part is nitrogen. That part, this part is nitrogen. Okay, so for at 25 degrees C, because that is your reference state. The reference state is at 25. So at 25 degrees C, where is it? Is it the inlet or the outlet? 25.
inlet.
Inlet. Okay. So we're going to go back to our 25 inlet. So enthalpy 0, 0. Why 0? Because that is your reference state. Okay. So now at 200, the outlet temperature is 200. So if we look at the value for nitrogen is 5.13. Can you see? Is it too small for you guys? Can see? Let me try to zoom if I can. I'm not sure whether I can zoom in. No, I can't. Anyway, you guys have the data with you guys. It's 5.13. This is nitrogen, 5.13. And for hydrogen is 5.06. 5.06. Okay. Now putting in the values inside this equation, if you put the value inside the equation, Q dot is equals to out plus out. So this is out. This is your sum of that sum over here. Okay, that's the sum. The product. So you have 50 mole per minute times by the enthalpy 5.13. What is the unit for enthalpy just now? Enthalpy is kilojoules per mole. Okay, kilojoules per mole. Kilojoules per mole. You can cancel the mole. plus, that is for nitrogen. Now for hydrogen, 50. I'm not going to write the unit because we already know how the unit looks like. So we're going to just multiply 5.06. Okay, that's, I'm taking it from the the outlet. That's your outlet. Now, oops, sorry. I don't have enough space. Minus, this is the inlet. So the inlet is going to be this part. So what's the answer for the inlet, guys? What's the product for the inlet? 50 times 0
Zero.
plus 50 times by 0. So that is your inlet. That is your inlet. Sorry. That's your inlet. This is your outlet. Now let's rewrite that. I'm going to go to the next page. I'm going to write it again, okay? In case you miss it, Q dot is equals to, it's now 50 times 5 point what? Can you give me the value? 50.13. 50.13. Plus 50. 5.06. That's your outlet. Plus. Is it plus or is it minus?
Minus, doctor.
Minus.
Minus.
Okay. Should be minus. Minus 50 times by 0 plus 50 times by 0. So what is the final value? The answer, the unit, if you look at the unit, the unit is more kilojoules per minute. If you look at here, the unit, after we have cancelled, it's kilojoules per minute. So this is going to be kilojoules per minute. So what is the answer? Anybody?
509.5.
5 point?
509.5.
509. That is in per minute. So let's look at the question itself. We have the question specifying that it should be in, it did not mention, but the answer here is kilowatt. This is the answer in kilowatt. So it's per second. So we're going to change the unit to per second. So we're going to change it to kilowatt. 1 minute, 60 seconds. Change that into kilojoules per second. So what's the answer? Anybody? Is it the same?
8 point.
Sorry?
8.483.
8.4?
83.
83.
Yeah.
8.483. The answer here is 8.49. Well,
It is 8.49
okay,
Yeah.
it's 8.49.
because the Q
Okay.
is 509.5.
0.5, yeah.
Yeah, okay. Okay, thank you. Okay. So we managed to get this exact answer. So that's how you do it. So let's briefly go through it. What you have to do when you start a problem like this, first thing, specify your basis. Okay? You don't forget your basis because you are doing material balance. Actually, what's coming in is equals to what's going out. So that's what you have to do. So you have to have a basis. Second thing, what you have to do is draw your block diagram. You need to draw your block diagram, label whatever is given, and whatever unknown, label it too. So in this case, the unknown is the amount of heat that you need to supply. Okay, the amount of heat that you need to supply is the unknown. You list down the temperature. You are operating at 1 atm, so put it down the pressure. Okay, your temperature coming in, your temperature coming out is given, so jot it down. Next, once you have managed to draw your diagram, decide, are you dealing with a closed system or an open system? If you're doing it with an open system, then you should be writing your equation for an open system. In our case, since there's flow coming in, there's flow coming out, there's input and output, then it's an open system. So you have the equation, write down the equation for your energy balance, which is the open system. When you do an energy balance, you need to specify the reference state. Do not forget to specify your reference state. You need to write it down. And if you are using a certain, if you're getting your enthalpies from a certain table, your reference state must be the same as that table. You cannot choose a different reference state. In chapter 8, you will be dealing with how to calculate the enthalpy. Then, when you calculate your own enthalpy, you will choose your own reference state because you are not referring to any table. But since in this chapter, chapter 7, you are referring to a table, you have to follow the same reference state. Okay, so don't forget the reference state. Once you have managed to write down your reference state, next what you have to do, solve for your energy balance. We already specified that there's no kinetic energy, there's no potential energy, and there's no shaft work. Reason is because it's just a heat exchanger. Nothing is changing in terms of the velocity. There's no change in the height, and there's no parts moving. So you cancel off the work, shaft work. So you end up with just Q is equals to the change in the enthalpy. So now you need to get the enthalpies. So the enthalpy, the equation for the enthalpy is always out minus in. This is the equation. Let me see whether I can get a different color. Okay. This is the equation for your normal change in enthalpy. Okay, out minus in. So this is why we draw the table. We have the out here and we have the in here. This is the product, which is that two product. And this is the product. This is the out of the product. This is out. This is in. Okay. So all you have to do is get the product. So this is 50 times by 5.13. That's the product of that two. And now do the same thing for hydrogen. That's 50 times by 5.06. That is the sum of this part, out. That's the out part. Now you do the same thing for the in part. So you do the same thing. 50 times by 0, that's the in for the nitrogen. 50 times by 0, that's for hydrogen. So you should get your final answer using that calculation. Any question? I got a lot of scribble over here. It's very messy. Any questions? Guys?
No question, Doctor.
No, nobody? Any question? So if you look at the problem, your final answer is going to be in kilowatts. Okay, so I'm going to go back to black. Yeah, no problem. No questions? Okay, since you don't have any question, let's see whether we have any more example. Let me see. There's one example from the textbook that is almost similar to this problem. If I'm not mistaken, is 762. Example 762. Let me find 762. Okay, that is example 762. Sure whether I can zoom, whether I can zoom in. Can you see the question, guys? Guys? Anybody?
Yes, doctor.
Yes.
Yes, okay. Now, in this case, you are again heating it up from 150 to 200 Kelvin. First thing, basis. Oh dear, why is it so big now? This is 1. 1 is big. Not sure how what is 9 is what? 9 is small. Let me see. I'm not used to this. Ooh, that's big. So I should be going 1. Okay. Okay. Your basis for this example, let's see. Did they specify any flow rate per kilogram of the mixture? Per kilogram of the mixture. Let me. Okay. You have a mixture, a liquid mixture, having 60% of ethane, 40% of butane. If you look at the component, ethane and butane, they are hydrocarbon. They have similar structure, similar, because it's it's just carbon and hydrogen. So they're very similar. So that means you can assume that you can use the pure enthalpy of each component, the enthalpy of each pure component. Just like what we did just now. Okay, now we're going to draw the first thing, basis. Basis. The basis is per kilogram input per kilogram of the mixture. So let's draw the diagram first before you write the basis. You have 1 kilogram. What is it? Is there any per second? Per kilogram? Is this per kilogram? per kilogram. Calculate the required heat per kilogram of the mixture. Okay, let's put in the per kilogram. So your basis 1 kilogram of the feed. That is your basis. Okay, so the mixture is 0.6 kilogram per kilogram. This is mass fraction of E10. So I'm going to write it as capital E. The rest is butane, 0.4 kilogram per kilogram of butane. I'm just write it as capital B. The same mixture is coming out because nothing is going, it's just one stream in, one stream out. So the same mixture is coming out. It's a liquid mixture. Okay. This is your heat exchanger. So definitely you're going to put in heat. The temperature coming in is 150 Kelvin. The temperature going out is 200 Kelvin. You are operating at a pressure of 5 bar. So we're going to write whatever is given. Anything else? Okay, next leg, the potential and kinetic energy. So you're not going to have any potential kinetic energy. The value of your enthalpy is given here. Okay, at a different temperature and pressure of the input and output. So now the question asks you to calculate the required heat. Since you are heating it up, so your heat should be coming in. So your answer should be positive or negative, guys?
Positive.
Positive. Okay. Now, we're going to get the answer in kilojoules. There's the answer here. Kilojoules per kilogram. Yeah. So this is going to be in kilojoules per kilogram. We do the same thing like what we did just now. So we're going to go to the next page. Oops.
Heat input per kilogram of the mixture.
We're going to have a reference state. Problem is this. I don't know what is the reference state. Why I don't know? Because this data is from a different textbook. From, if I'm not mistaken, the author of this textbook, he specified that it is from Perry Chemical Engineers Handbook. So it's from Perry Chemicals Engineer Handbook, and the author did not specify what is the reference state. So we don't know what is the reference state. So we cannot write the reference state. That's the problem. It's not specified in the example what is the reference state. The author should have mentioned what is the reference state. So that's we don't have the reference state. By right, the author should have mentioned it. So I'm going to draw the same table. So since we don't have the reference state, we just, it's not possible to write it down. Yeah. So let's get this done. Okay. Now I have ethane. I have butane. I have my mass coming in. My mass is in kilogram. I have my mass in. This is in. This is mass out. In kilogram. Okay. My specific enthalpy is, what's the unit of specific enthalpy? Let's have a look. Kilojoules per kilogram. Kilojoules per kilogram. So write down the unit. That is my specific enthalpy, kilojoules per kilogram. Don't forget about the subscript. This is out. This is in. Okay. So now what's the value? Let's look at the value. Oops. At 150, that's the in. So that's in. That's in. For this is ethane, 314.3. 314.3 is for butane. This is, sorry, not butane. What is it? Ethane. That is ethane, C2. And this is for butane. So you have the enthalpy given, 314.3 for ethane, 314.3. I need to cancel that. Okay. 314.3. And let's look at that value just now. It's 30. That's 30. Okay, so do the same thing for the outlet temperature. The outlet temperature, if you look at this, that is the temperature outlet. That's the outlet temperature. That 434. This is for ethane. This is for butane. So 434.5. And for the butane, 130.2. Let me tidy up a bit. Okay. Oh, somebody? What did I do wrong? Anybody?
It's enthalpy.
Yes. What I'm doing is I'm writing the values inside the mass in kilogram. It should be in enthalpy. 314.3, 30, 434. How come nobody correct me? You guys just keep quiet. This is mass. This is mass. That is mass. That is mass. Okay, now we need to calculate the mass. Yeah, tidy up a bit. Okay, now let's look at the value. What is the mass, guys? For ethane? Anybody?
0.6.
0.6. Okay. You have the same amount coming in, the same amount going out. So this is your mass fraction, 0.6 for ethane, 0.4 for butane. So this is 0.6. Oops. What's happened? What can I write? Why can't I write? I can't write 0.6. What happened? Something wrong? 0.6? Okay. Let me erase that. Something wrong. Yeah, let me erase it first. Okay. 0.6 and 0.4. I hope I can write it. Nope. Oh dear. 0.6, 0.6, 0.4, 0.4. Now, what system are we looking at? Anybody?
Open system.
Open system. So do your energy balance for an open system. Yeah. Kinetic energy, potential energy. Potential energy equals to your heat flow rate and your shaft work. Again, because we are dealing with heat exchanger, there's no parts turning inside your system. There's no potential energy. There's no kinetic energy. It's already stated in the problem that you can ignore kinetic and potential energy. So your heat coming in is equals to the change in enthalpy. And this time you are dealing with mass. So without mass times by specific enthalpy minus in mass specific enthalpy. You don't have the dot there because it's in kilogram. I don't see the problem did not specify it's per second. There is no rate. It's just per kilo. It's just per kilogram. It's per kilogram. So I think it's just mass. It's not rate. So let's do the calculation. We're going to put in the values. Out 0.6 times by the kilogram times by 4.5. The unit is kilojoules per kilogram. Okay, that is for that part.
Kilo.
For this part. Now do the same thing for your butane, 0.4.
Kilogram per second.
I'm not going to write down the unit because I already have the unit over here. That's kilogram. Cancel off. 130. The problem with writing using this the iPad is that's the problem. That is your out. The product of your out minus the product of your in.
Specific enthalpy.
Okay, your product of your in is 0. This is your in. 0.6 times by its enthalpy 314.3 plus the the flow of butane, and its enthalpy. So everything is there. So what's the final answer?
112.2.
Sorry,
112.2.
112.2. Let's see whether it's the same as what is given in the problem. 112. There's no point. Why is it in kilojoules per kilogram, guys? Why is the answer in kilojoules per kilogram? When we did the calculation, we got just, what did we get? We just got kilojoules. Why is our unit not the same as that given here, kilojoules per kilogram?
Doctor, because it's only 1 kilogram, so
Yeah, because you're using per kilogram. Your basis is 1 kilogram. So even though your unit here is only kilojoules, you say for every 1 kilogram of your feed that you are feeding into the heat exchanger, the amount of heat that is coming out that it has to be supplied is 112.2 kilojoules. So you can specify it as this, or you can also write it as kilojoules per kilogram, because your basis is 1 kilogram. So that means 112 kilojoules per kilogram. Is it clear?
yes.
Yes.
Yeah, good. You know how to, now that we have done 2 examples of the same similar mixed kind of procedure. Anybody have any questions? Any questions?
Doctor, just regarding the reference state here in this question, compare, if you want to compare that to the previous one, there we chose our own reference state, but here is it because
You cannot choose
here,
your own reference state.
oh, so here why we didn't even choose any reference state?
Because
Is it
because the problem, the data that you get, hold on, let me go to the first page. This data, let me put it in a different color so that we can see. Okay. This data that is given, that is from a textbook, from a book named Perry Chemical Handbook. It's stated in the text, in your textbook, it is specified that it is from Perry Chemical Engineers Handbook. You need to go to that book and look at the table and find what is the reference state.
Oh, I see.
To find that textbook and find the what is the reference state from that textbook. The reason is the author of this the author of our textbook did not specify what is the reference state, so we don't know.
All right, sure.
Okay. Any other questions, guys? Any other questions? Okay, let's look at this. This is not a typical unit for energy, isn't it? Energy is always kilojoules or kilowatts. So this per kilogram, because just now we are using that as our basis. Okay, now it's already almost 3 o'clock. Would you prefer us to have a break of 5 minutes, or would you prefer for us to continue? Anybody?
I prefer break.
Yes,
Break.
please. Okay,
Yes,
come
yes,
back
please.
at 5 past the hour of 5 past 3. 3 or
Okay.
5.
Thank
Okay,
you,
guys?
miss.
Okay, I will unshare this and we'll come back 5 minutes past 3. Okay, have a break. Take 5.
required heat input per kilogram. Required heat input. Required heat input per kilogram. Per kilogram. Oh, boleh tukar jadi kilogram. Maksudnya 1 per minute. Yang ni kg per second. Tapi dalam ni dia nak dalam per kilogram. Kat dalam ni jawapan dia nak dalam heat required. Heat required general. So ini kg per minit pula. Oh, heat required tapi bukan Q but not per kilogram. Dia flow rate. Flow rate of Q. Q dot. Okay, ni Q dot. Kalau kat dalam ni heat input per kilogram. Spesifik lah. Q spesifik. Oh, okay. So first kita ada Q dot is equals to 112.2 kg per second. Kalau Q ni equals to 112 kilojoule per kilogram.
Hello, doctor. Doctor.
Yes.
Doctor, can I request something like, can you record the classroom videos? Because like just now,
Record it. Why? Why? May I ask? Who's speaking, please? Hello? May I know who's the one that requesting the recording? Excuse me, who's speaking? Excuse, can you hear me? Guys?
Yes, doctor. Yes.
Who's the one that is asking for me to record it just now?
Doctor,
Yes?
having problem with phone.
Sorry?
Having problem with the phone.
Having problem?
Yeah. Cannot. Not listening.
Can hear, is it? Can you hear me?
Yeah, we can hear
Guys?
you.
We can hear you. It's clear.
It's clear. Then who's the one that is having problem? Who's the one that request just now? You mean just now when I was having the lecture, you can't hear it? Somebody, who's the one that is requesting for the recording? Because I don't know.
I think she
Let
wants
me
her to
see.
record. I think she wants you to record the class so we can watch it after the class for
Oh,
revision.
she has the classes is clashing, is it?
No, I think
God,
it's just for future revisions so we can watch the class again.
for future. Your textbook is what my lecture is exactly the same as the textbook. So I don't see the need to record. The reason is my lecture is just looking at the example from the textbook. If you don't know how to do, if you don't understand my lecture, you can ask during the lecture. And if you still don't understand, have a look at the textbook. That's the reason why I don't want to record. I might have a few examples that is different, but once you have look at a few examples, you will have a rough idea of how to go about it. That's the reason. And another thing is that I don't prefer not to record is because I don't want people not to come to class. You come to class unless you can't avoid it. Unless you can't avoid it because you got you are not well on that day or due to certain unavoidable circumstances, but not because of having clashes, different classes at the same time, then that's not a wise thing to do. That's the reason why I don't want to record.
Oh, good afternoon, doctor. So I was the one speaking, and I had an internet connection problem, so that's why my connection just dropped. So actually, like I wanted to attend the class. Yes, definitely I want to, but due to some problems, I couldn't attend the class. So that's why I feel like if it would have been recorded, I wouldn't have missed what actually I missed just now a few minutes back. Then after that, actually I recorded myself, like because I was driving. So that's why doctor has suggested like sometimes some of them we might have problems coming in that we couldn't predict. So I thought of recording. That's it. That's a suggestion.
Why are you not seated? Why are you not seated? I mean, why are you driving?
Yeah, because I was the only one here, and then my mom, she went to fetch my sister, and then she wasn't here. So I had to go myself to deal with the problem, the issues I was having. So, and then because I don't use my laptop is also the camera is not good and it's also laggy when I use VBAX. So I use VBAX through my phone. So when my phone has problem, so that's why now I have to face this situation.
Okay, the reason you are having problem is because you are out on the road. You are not properly seated at home or somewhere whereby you have access to your computer. So I think you have to make an arrangement where when you have class, then you need to be, have everything is there. You're having the internet problem because you're on the road.
Actually, this area where I'm living, I'm already having internet problems. It's Kampas rural area. So actually, there is also, I'm using Johor Wi-Fi to connect, and the connection will disrupt every 30 minutes. I have to. So that's why it's just suggestion. It's okay, doctor. If you prefer not to record, it's fine. Then.
Yeah. Frankly speaking, I prefer not to record because I like the student to attend the class.
Yeah,
And,
I understand that too.
Yeah. And if you
It's
don't
fine. Thank you,
understand,
doctor.
then you have the textbook that you can refer to. If you don't have the textbook, you have the e-textbook from the internet, which is free, the third edition. But still, the only thing that's different between the third and the fourth edition is the sign convention for the work. That's all. I'm sorry, I'm not going to record. Okay? The reason is because I want you guys to be in class, even though you are at home, but be online during class time. That's the reason. Okay? So if you have any problem, you can ask me using WhatsApp. If you have any problem, if you want to, if you want a copy of the example that we have done, I can forward it to you using WhatsApp. But I'm not going to record. Okay, guys? Okay, now let's go back to our slide. We need to look at more examples. So I'm going to use my iPad again and see what example can we look at. Just now we did 2 examples. How about we do one of the example from the textbook, example 753. Not sure whether it's possible for me to enlarge it. I'm having problem trying to enlarge this thing. Whether I can get it enlarged because I don't think you can see the theme table. Yeah, this is the problem. Still not that really visible, but at least better. I'm not sure whether you can see it from your side, the theme table, but this is from appendix B7. So if you have the textbook or you have the online version, the internet, the e-version, you can still you can go to table B7 and have a look at the steam tab, superheated steam. This is superheated steam. This is superheated steam. Not so that clear because it's just the print is too fine. Yeah? But we try to get the most out of it. Okay, let's look at the problem. You have a new term here, which is superheat. And if you look at the definition for superheat, that's the definition for superheat. The difference between the actual temperature and the saturated temperature. So superheat is equal to the actual temperature minus T saturated. Okay, so here the value is given 190. Okay. We have steam at 10 bar. So if I look at the steam table, that is 10 bar. Okay, that's 10 bar. Now I'm going to undo that because I need that temperature. Now let's see whether I can enlarge it. Try to enlarge. Oops, I messed that up. I'm trying to enlarge. Okay, guys, it's quite enlarged now. This is the 10 bar. Oh dear. Okay, let's have a blue color. Okay, this is 10. Oh, that's 10. That's the amount, the region that I want. Okay, 10 bar, and the temperature, saturated temperature is 179.9. That is your saturated temperature. So let's go back. I don't want highlighter. I want it to be pen. Wow, how I'm going to get my pen back? I don't want highlighter. I'm having difficulty here. Oh, sorry guys. This I'm not used to this. I'm not used to this app because before this I was using a different app. So right now I'm having difficulty now. I need to go back to my. Okay, now I know why. Okay. So your saturated temperature, T saturated at 10 bar is given here 179.9 degrees C. Yeah. So that is the saturated temperature. Now I need to zoom out. I really need to zoom out. Okay. So your superheated just now, this is the equation. So your T actual is equals to 190 plus T saturated, and that's going to be 190 plus 179.9. That's roughly 180. That's 180. So what's the answer? Anybody? What is the actual temperature?
269.9.
169.9. That's about 270. Okay, 270 degrees C. That is the actual temperature of this problem. Let me try to drag down. Okay. Your steam is at 270. Your steam is at 270, superheated. Why is it superheated? Because the actual temperature is beyond the saturated temperature by 190. So now you're going to feed that steam to a turbine. The flow rate is 2,000 kilogram per hour. The turbine is operating adiabatically. That means there's no heat loss. The outlet stream is saturated at 1 bar. Calculate the work in kilowatt. That's the problem. Let's do that in kilowatt. Ignore kinetic and potential energy. Okay, let's look at the problem now. You have steam at 10 bar, 190 superheat. That means the actual temperature of your steam is beyond 190. Sorry, beyond the saturated temperature by 190. Your actual temperature, this is the actual temperature. Oops. That's the actual temperature. You need to calculate your actual temperature, which we did. We managed to get 270. And at that temperature, you're going to feed it to a turbine at a flow rate of 2,000 kilogram per hour. And your turbine is operating adiabatically, and the outlet stream is going to be saturated steam at 1 bar. So now you need to ignore kinetic and potential energy and calculate the work that the turbine will be giving off, or the output work. So now let's go to the next page. Not the next page. There's still some space here. I just need to get it zoom out. Is it possible for me to zoom out? No, I'm having difficulty zooming out. Okay, let's. Now it's already zoomed out. Okay, let's. First thing first. What do you have to do? Anybody?
Write out the formula of open system.
What? Sorry?
Write out the first law from dynamic for open system.
No, the
Okay.
basis. Right, the basis.
Basis. So write down your basis. What is the basis? First thing first, write your basis. What is the basis?
2,000 kilogram.
2,000 kg per hour.
Okay, kilogram per hour of your feet. Your feet.
The
Okay?
temperature is wrong. 370.
Temperature is wrong. Why is the temperature wrong?
370.
200 and?
370.
Oh dear. Come on, guys. Do the calculation, please. Check the temperature.
It is 369.9.
370, isn't it?
Yeah, 370, yes. 370, yes.
Yeah.
It's 370.
Yeah. Okay, check your temperature. 370. Okay. So now, once you have your basis, what next? What to do next?
Draw.
Draw the diagram. Okay. Draw your diagram. Now you have a turbine. You have coming in and you have an outlet coming out. This is a turbine. You're going to give off shaft work. And that unit is going to be in kilowatt. Going to give off shaft work, okay? The amount coming in is 2,000 kilogram per hour. Okay, the amount coming out is also still 2,000 kilogram per hour. The only thing is that this is at a temperature of 370 degrees C, and this is saturated. It's specified that it's saturated steam, and at 1 bar. It is at 1 bar. This is at 1 bar. I don't have space to write. I better undo this. I need space. Yeah, this is 1 bar. Okay. So the input is superheated steam. This is your work coming out. So that's the question. This is adiabatic. This is adiabatic. It is adiabatic. So Q equals to 0. What's next? What's next?
The equation.
Equation. Okay. Let's look at the next page. Write down the equation. What equation are we going to write?
Open system equation.
Open system. Okay. That's different in enthalpy, kinetic energy. You should now be very familiar with this equation because we have been writing it over and over for the example. So everybody should know how to write this equation. You don't need to, use your textbook to check this equation because it's so, we have repeated so many times already. Kinetic energy we ignore, potential energy we ignore, we say it's adiabatic, so that's 0, Q equals to 0. So we end up with the final equation of work is equal to a difference in the enthalpy. Again, the difference in enthalpy, we have outlet minus inlet. Okay, the thing is we are looking at mass. Is it mass flow rate? Is it mass or mass flow rate?
Mass flow rate.
Mass flow rate. So write a dot on it. Mass flow rate with a dot on it. And you have your specific enthalpy. Yeah. You have your mass flow rate, not mass. Just mass flow. There's a flow rate there. Okay. Now, we need to get the enthalpies. What you can do is you can draw your table. That's what we did just now. We have steam. No, better not use table because it will be not use table. Just look at the diagram. We have in 2000, 370 degrees Fahrenheit, and it's superheated. First, the easiest one will be looking at the saturated steam at 1 bar. Look at this condition, saturated steam at 1 bar. So let's try to zoom in. I'm having difficulty here trying to zoom in. Oh dear, why I'm not having any? Let's see whether I can zoom in. Oh dear, how to zoom in? Anybody have the table with you guys?
Yeah, doctor.
Okay, read for me the value of the steam table. Okay, right now I managed to zoom it in. Where is 1 bar? That's 1 bar. Okay, that's 1 bar. Saturated steam or saturated water? The outlet. Is the outlet saturated steam or is it water? Anybody? Steam. So you should be here looking at saturated steam. Where is the enthalpy? That's the enthalpy. Okay, that's the enthalpy. 2675.4. That is the enthalpy for 1 bar at 1 bar for saturated steam. And the other, that is for the outlet. Okay, write it down. 2675.4. That's the unit is in kilojoules per kilogram. Now let's go and look at the enthalpy for the inlet. Why am I not getting it? I need to move it. Okay, let's move it. Where is the inlet? The inlet is at 370 temperature. 370. Where is 370? This is 300. This is 350. That is 400. At what is the pressure, guys? Anybody? What's the pressure of the inlet?
10 bar.
10 bar. Let's see. Where is ouch. Keep on getting the screen. Because my finger, I seems to be, I don't have a good contact. Okay, 10 bar. This is 10 bar. 10 bar. Your temperature is 370, so we need to go at 370. The last, this is 350, that's 400. You need to interpolate between these two values. Oops. Between that two values. I can't even get it to look, Okay. What's the value? I can't even get it. 30, is that water? It's 31.5, is it? 3159. 3159, 3159, and 3264. We need to interpolate because that temperature is not 370. This is 350 and 400. So we need to interpolate. Then let me zoom out. Which I'm having difficulty here. Okay. So next, go to the next page. Write down what we have. We have what we have right just now. At 1 bar saturated steam, the enthalpy. What did we get it for the enthalpy? Anybody? Anybody?
2675.4.
Yeah, from that value. Yeah, I can't read it now because just now I zoom in, but now I'm not going to zoom in. Can you please repeat that?
75.4.
75.4. Okay, the unit is kilojoules per kilogram. That is your outlet enthalpy. Your inlet enthalpy, superheated steam at a temperature of 370 degrees C and 10 bar. What did we get the enthalpy now? We need to interpolate. That's the problem. We haven't get any value yet. Okay, so what we have a temperature of 350. 370 is the temperature we desire. We have 400. This is your temperature in degrees C. This is your specific enthalpy. So I need to read from the steam table, but I need to go again back to my steam table. I need to zoom in. Okay. Not doing it very well. 3159, 3264. Take note of the values, please. 3159, 3159, and 3264.
Doctor, I think it's 32001.
Okay, you already interpolate, is it?
Yeah.
Okay.
But if someone double check, that would be fine.
Somebody double check, please.
Yes, doctor.
Yes, I'm doctor.
Yeah. Okay. So it's 3, 2. Sorry. What's the value?
3159.
3159.
This one. 3159.
Is it?
320.
No,
It should be.
3264 and 3159.
No.
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 3201.
Okay. Somebody double check your calculation. Yeah, I think somebody made a mistake. 3201.
01.
Okay. That's the enthalpy at 370. Yeah. So that's 3201 kilojoules per kilogram. So if you write that in your block diagram, if I can, here is my enthalpy. Specific enthalpy 3201. I write the unit kilojoules per kilogram. Yeah, over here, my specific enthalpy is now, what was it just now? Let's see, what did I write over? Is 2675. 2675 kilojoules per kilogram. Yeah, so we have the enthalpy already. Well, guys, what's next? What's next? You already managed to get the enthalpy. What's next?
Substitute, I think, in the equation.
The what?
What?
Substitute inside the equation?
Find the change in enthalpy.
The open system equation.
Okay, before you can do that, there's something that you need to do. But, which?
The reference state, doctor.
Yes, reference state. So, I'm going to go to the next one. Yeah, I'm having problems scrolling up. Okay, reference state. What is your reference state? What is your reference state? Anybody? What is your reference state?
From the table.
From the table. And we are using steam table. So what is the reference state of steam table? Anybody?
I'm not mistaken, 0.00611 bar and
That's one bar. Okay, then
0.01 degree C.
you see again the state. What is the state?
Mixture.
Liquid water. It should be liquid water. Have a look. When it is at that temperature and pressure, the enthalpy of the liquid water should be 0. Okay, so the pressure and the temperature is known as the triple point. Triple which? I don't want to. Okay. Triple. I'm not getting my L. Point. Okay. Triple point. Your pressure at 0.00611 bar and a temperature of 0.01 is known as the triple point. You can write triple point for liquid water. But if you want to write the whole thing, fine, that's good. So now, let me draw again the same diagram because initially it was crowded on the, on the first page it was really crowded. So I need to draw again. You don't have to draw again. I just need to draw because I want to show to you guys this is the enthalpy that we got just now. That's the enthalpy that we got just now. Let me look back again at my first page. 2675, 2675, and that is kilojoules per kilogram. And my inlet enthalpy 3201. Okay. 3201. 3201 kilojoules per kilogram. Okay, your equation just now, what did we manage to get? Let me undo that. I'm not going to write the whole thing. We're going to have, if you look back again to the equation just now, where is the equation? That's the equation. QS. The equation is QS.
So the temperature.
You don't need to repeat the whole thing. QS is equals to out. This is mass flow rate times by specific enthalpy minus in mass flow rate times by specific enthalpy. Yeah, so since your mass in and out is the same, you can take it out. Take it out from the bracket. So this is going to be out minus in. Okay, so what is the mass that we have? We have 2000 kilograms per hour. Yeah, the difference in enthalpy, out enthalpy is, this is out enthalpy 2675 minus the in enthalpy 3201, and the unit is kilojoules per kilogram. I forgot to write kilogram here. Per kilogram. Something wrong. What did I do wrong? Here, that unit cannot be kilogram. It's per hour. Okay, so you can cancel your kilogram. And if you want it to be in kilowatt, then you need to change it into second. Yeah, so what's the final answer for your work? Shah, what is the final answer? You need to put in take out. It depends on the symbol. Yeah. What is WS? Anybody? What's the answer?
Enthalpy kan? Okay, enthalpy.
Guys?
Doctor, negative 292.
Negative
-292.
292 kilowatt, kilojoules per second. Anybody get a different value? Did all of you manage to get the same value?
Yes, negative 292.2.
Okay. The symbol negative indicates that work is
System.
getting out from the system. The turbine is giving off work. If the turbine is doing work, okay, it's turning the turbine is turning the shaft. Okay, so that's why it's negative. Your arrow should be pointing outward. Okay, any question on this? Any question? I did not draw the table. I did not tabulate it because it's so easy. You have one enthalpy coming in, you have one enthalpy coming out. You really don't need to have a table. It's not a mixture. Any questions? Just ask. I have the whole thing written here. If anything you need to find, anything you need to clarify. The problem with this example is that you need to interpolate, which we did. You guys did interpolate for the enthalpy. And another thing that is different from the previous example is the statement of superheat. The statement of superheat. We need to know what is superheat all about. That's the statement of superheat, degree of superheat. You need to get the actual temperature of your superheated steam. Okay, anything that you need to ask? Any guys? Any questions? Anybody?
Doctor,
Yes.
the reference state I can't find it in the table.
Sorry, I can't hear you.
The reference state
Reference state, yes.
I can't find it in the table.
Okay. This is superheated steam. When you look at B7 is superheated steam. Your steam table is the superheated steam and the saturated steam table is the same thing. The reference state is the same.
Superheat and the
Superheated and saturated. So if you look at steam table, let me see whether I need to close this. I go back to a steam table. I have a steam table over here. Okay. Let's zoom in. This is saturated steam, B5. Okay. Where is enthalpy? When is it 0? 0. Where is the pressure? That's the pressure. Where is the temperature? That's the temperature. Let me use the highlight. Okay, that's the temperature. That's the pressure. That's the enthalpy when it's 0. Even though it is stated that this is saturated, but when you're using superheated steam, you use the same reference. Your superheated steam and your saturated steam has the same reference state. Any question? Again, other questions? Is that clear? Oh, who's the one asking this now? Is it clear about the reference state?
Hey, doctor.
Yes, doctor.
Okay, good. So your reference state is that value, temperature. That's the pressure. Why is it the reference state? Because when it is 0. Well, this is what? This is liquid water. It's not steam. This is liquid water. We need to specify the state. Because when you look at steam, it's not 0. It is liquid water, then it becomes 0. When it's steam, it's not 0. Any other questions? Any other question on that problem just now? Where is the problem? This is the problem just now. Any other questions? No problem? No, good. So the time now is about 3:38. Let's continue. Let's look at this example. See whether you can start. What is the first thing to do? Example 761. You have 2 streams being mixed to form the feed to a boiler. Yeah. your exiting stream goes through, oh, this is a very long example because you've got to calculate the kinetic energy. There's a pipe diameter given. Calculate the required heat to the boiler in kilojoules per minute if the steam that comes out is saturated. Neglect the kinetic energy of the inlet stream. Oh, this is going to be long. This is going to be long. Let's see whether we have a shorter example because the time left is about a few more minutes. Let's see. This is 763. 763. The example 763. Is it long or is it short? Let's have a look at the textbook. Oh, that's short. That's a very short one. Okay, let's look at this example then. Saturated steam. Let me zoom. Okay, saturated steam at 1 atm, saturated steam at 1 atm is discharged from a turbine at a rate of 1,150 kg per meter. Superheated steam is needed at 300 degrees C, 1 atm, as feed to a heat exchanger. That's the feed. You need to, what do you need to do? Understand the question first. Saturated steam at 1 atm is coming up from a turbine. So let's draw. This is a turbine. It's coming out. That's saturated steam. Superheated steam is needed. Okay, I need to undo that because I don't need this. Can you read the question properly? Because it's just mixed. It's mixed. Oops. The turbine discharge is mixed with the superheated steam. So this is a mixer problem. You get one stream being mixed with another stream. And you're going to get another outlet stream. So what happened here is that you have saturated steam mixed with the superheated steam. Is that it? The turbine discharge is made with superheated steam available from a second source. And you're going to produce a superheated steam. Did I get it right? Come on, guys, check whether I got it right. This is adiabatic. This is a mixer, it's adiabatic. And let's see. Calculate the amount of superheated steam at 300. Okay. This is your superheated at 300 degrees C and 1 atm. You're going to have another superheated steam at a temperature of 400. This is going to be at 400. And what is the temperature? 1 atm. Your saturated steam is at 1 atm. Okay, now that rate is 1,150 kilogram per hour. And that is going to be mixed to superheated steam at 1 atm. The mixing process is you need to calculate the amount of the 300 produced and the required volumetric flow rate of that steam. What is this volumetric flow rate? What is this mass? That's the question. Anybody? Did I get it right? Have a look. Oops. Did I get that right? Somebody check. Anybody? Guys?
Can you show the question again?
Okay, I'm seem to be talking to myself. Okay, let's look at the question. Saturated steam. Okay, let's display this. Saturated steam is discharged from a turbine. There's a turbine here, somewhere here, there's a turbine. Okay, there's a turbine. This saturated steam is coming from a turbine. Okay, and that saturated steam is at 1 atm, having a flow rate of 1,150 kilogram per hour. Your superheated steam is the one that you need. You need this superheated steam. The one coming out here is the one that you need. You're going to feed it to a heat exchanger. So you need it to be at 300 degrees C, 1 atm. the turbine, the steam from the turbine is going to be mixed with another superheated steam. So I'm going to push this up. Okay, this is another superheated steam. The second stream here is another superheated steam. It is at 400 degrees C and 1 atm. I'm going to mix it and produce this outlet's superheated steam. That's the question. Is that correct? Let's have a look at the question. Is that correct? The mixing unit is adiabatically. It is adiabatic. So you have this second source of superheated steam. You're going to mix it with the one from the turbine, saturated steam. And it's done adiabatically. Now, what is the amount of output, the amount of the steam produced and the volumetric flow rate of the steam superheated steam? This is a very complicated problem actually, because you have only one mass flow rate. You don't have the other flow rate.
Like what if I prefer mass balance first?
Yes, you need to solve for mass balance, but you have two unknown for the mass balance. You don't have this mass balance, you don't have that mass balance, you don't have. So this is, for example, this is equals to mass flow rate 1, not mass balance. This is mass flow rate 2. This is mass flow rate 3. You don't have it. You have two of it unknown. First, before you can do it, what is your basis, guys? What's the basis?
1150.
Yeah, 1150 kilogram per hour of superheated steam. Oh, sorry, saturated steam. Yeah, that's your basis. You have to do mass balance, but you still cannot solve for the two unknown, the flow rate of the two stream, because it's not enough. Only one. Can you solve it really? If you write the mass balance, let's see. If you write the mass balance, let me write down. You have a basis already. Your M1 plus M2 is equals to M3. Your M1 is 1150 plus M2 equals to M3. Can you solve it? Can you solve it?
No, because
No.
two unknowns.
Yeah, got two unknown. Look, you cannot solve it. You have two unknown. I'm going to just display this so that you can have a look. M1 is coming in, M2 is coming in, M3 is the output stream. You cannot solve it. You need to do it simultaneously with energy balance. Yeah? So now, you need to do it using energy balance, so you need to have a reference state. So what is your reference state, guys? Anybody?
Triple point, right?
Triple
Triple
point.
point, because you're looking at steam, superheated steam, saturated steam. So it's going to be triple point. Triple point, liquid water. Write down triple point liquid water. So now you have look at the diagram. You have saturated steam at 1 atm. You need to get the enthalpy for that saturated steam. This enthalpy, you need to get this. Now we already give it a subscript 1, so we're going to stick mental with 1. You need to get the enthalpy of this, another enthalpy for 2. That's the stream coming in, and you need to get this enthalpy for the stream coming out. That's number 3. You have the temperature given. You should not have any problem getting the enthalpies. Okay, let's look at the enthalpy for saturated steam at 1 atm. Zoom out. 1 atm. This is roughly 1 atm. This is roughly 1 atm, even though it's 1 bar. It's roughly. So what is the saturated enthalpy of steam at 1 atm? Anybody? Can you read the values?
2675.4.
Yeah, 675. That is it. 2675.4. Okay, for the other value, superheated steam, you cannot use the saturated steam table. You got to go to the superheated steam. This is the superheated steam. Oops. This is superheated steam. Okay, now at 1 atm, 300 degrees C for that temperature and pressure. 1 atm, that's roughly 1 atm. 300 degrees C. Is there 300 degrees C? No, just 400. I don't have 300 here. Okay, let's look at superheated steam at 400, 1 atm. 400, 1 atm. Oops. 1 atm, 400, that's 400, 1 atm. So that's the enthalpy. H2. Let me, oops. Sorry guys, I'm having problem here. This is the previous one. What's the time? It's almost time. I think we need to stop because it's almost time up. So let me just write down. That is the value. What that value is now? Can I zoom in? Or I can't zoom in.
3278.
3278 because I'm having problem. Yeah, that's at 400 degrees C. This value just now, what was it just now? 2, what? Sorry. H2 something. Anybody? 2675.4, isn't it? The saturated steam.
Yes.
Is it right?
Yes, yes.
Yeah. So for the superheated steam at 300 degrees C, 1 atm, can you read it off from the table? Anybody?
3074.
Well, that value, you need to write it here. Anyway, it's almost time up. So we're going to look at this next week because it's quite a big problem because it's not really big. It's just that you need to solve the material balance and the energy balance simultaneously. When you have the material balance, the material balance is not enough for you to solve it. You need to get the energy balance in order to solve for the unknown. Okay, so when you do the material energy balance, you will also have the unknown M2, which is multiplied by that, and then M3 multiplied by its specific energy. So you will solve simultaneously the material balance and the energy balance.
Can I get the state of the M3?
Can you, sorry?
The state, the temperature and the pressure of M3.
Okay,
Yeah.
if you want to give it, yes, please. Let me go here. So what is that value? Did you manage to get the value?
I'm trying to solve the.
Sorry?
I'm trying to find the mass.
No, you can't get the mass yet.
No, it's like two equation. I have two equation.
Okay, look. I'm going to give you a rough idea of how to solve it. Yeah? Your energy balance is going to be, as usually, is going to be, everything is, let's have a look. It's adiabatic. It's adiabatic, Q is equal to 0. It's a mixer, that means no shaft work. Okay? There is no potential energy, there's no kinetic energy. So what do you think is the final equation?
H equal to 0.
Equals to 0. Okay? So that means out. And this is mass flow rate minus in. Mass flow rate, enthalpy. You need to get all the enthalpies values from your steam table. Either it's superheated or whether it is saturated. You can get it from the steam table. So now, the only unknown is the mass of M1, M2, and M3. You already managed to get the enthalpies. So everything is equal to 0. So now you can solve for your unknown using the material balance and the energy balance. That's how you do it. But we don't have enough time to finish it. So I thought it was a short one, but it's quite some time because we need to find the enthalpies for the outlet stream. We haven't done that yet. We did not get this yet. We managed to get 2 enthalpies done, but we can get that value. The enthalpy of the outlet stream, we can get it from the steam, superheated steam, because we have the pressure and the temperature. Everything is available except the mass, which is M2 and M3. Okay, so if you look at the diagram, you have M3 times by H3, that's your outlet, minus your inlet, M1, H1, plus M2, H2, your enthalpy 2. So everything enthalpy is available. The only unknown is M3 and M2. Okay, guys, it's almost time up. So any question, if you have any question, we will look again at this example. We will look at it next week. But for those who already know how to solve for it, without looking at the example, find the enthalpies for H3, which I haven't done. We already managed to get that done. We already managed to find the enthalpy. M1, we already have that value. We don't have M2. We don't have M3. So using this energy balance, solve it using and simultaneously with the material balance. You should be able to solve for M1 and M2 and M3 because you got two equations, two unknowns. That's how you solve it simultaneously. This is your one equation, that is your second equation. Two equation, two unknown. Solve simultaneously. Any questions? If you want to do it, go ahead. But I will look at it again. We will look at it again next week, next Monday. Start from 8:15. God willing. Okay?
Doctor,
Yes.
will you share these notes and the e-learning?
Oh.
The solution notes.
I can show it using WhatsApp because I don't think I can upload. I'm not sure whether I can upload in e-learning because I need to. I can only share, upload. Can I upload? I'm not sure whether I can upload.
I think WhatsApp is okay.
WhatsApp is okay. The problem is now, this is a different WhatsApp that I use. I mean, this is a different apps. This app is not the one that I used before. This is it's a different app. The one that I have in my handphone, I can change it to I can upload in WhatsApp. But I can snapshot it. I can really snapshot it and have it in WhatsApp. Okay?
Okay, Doctor, thank you.
Welcome. Anything else? Okay, guys, that's it for today. I do apologize if there is any shortcoming in my lecture. There's always something new because this is not our norm to have an online lecture. We are learning. I am learning with all this that I have to teach using my iPad. So everything is quite difficult because I have to display everything, and unfortunately, that's the circumstances that we are in. So any shortcoming, I do apologize. And thank you for coming. And I hope if you have any problem, if you want to ask, if you are shy in asking during the lecture, you can ask, personally using WhatsApp. Okay, thank you very much, guys. Assalamualaikum warahmatullahi wabarakatuh.
Thank you, Doctor.
Thank you, doctor.